Space Agency. So without further ado, I would like to give the floor to our first speaker, David from Materion. Thank you very much for being with us today. The floor and the next 10 minutes of everybody's attention is yours. Let me remind you to stay on the red spot if you want. We like the epic spot. The floor is yours.
All right. Good morning, everyone. I want to thank the folks at EPIC for having me here today, and for also for ESA for hosting us. So I want to start off telling you a little bit about Materion itself. In addition to our precision optics group, we have a number of other connective technologies that link to the space community. Those include our beryllium products, specialty alloys and metals, and advanced materials. So our precision optics group comes from two main sources. Bar Associates, which was acquired in 2009, and then EIS Optics in 2011. Between the two, we have one of the largest precision thin film manufacturers in the world, with over 100 deposition systems. We operate from the UV as low as 180 nanometers all the way up to 50 microns. Now that covers a lot of different applications, from thermal imaging and night vision to astronomy filters, and of course Earth observation and LIDAR and free space communications. Our core capabilities cover three main areas: our deposition technologies, our clean room and glass processing, and then our component manufacturing. Because we work in such a broad wavelength range, we're very familiar with all different types of optical substrate materials and optical coating materials as well. So our space flight heritage spans over 40 years. We've supported all major industrial customers and primes, making different bandpass filters, edge filters, beam splitters. These have supported remote sensing and Earth observation applications, and LIDAR, free space, and deep space exploration as well. Some of these are discrete filters, and the focus of what I'm going to talk today, though, are multispectral arrays. And everything I'm going to discuss here is fully space qualified and rated at TRL 9. So the UV through long wave arrays. So multispectral arrays have been around for 35 plus years. The bulk of these, I'll say, have been more in the VIS and near IR range, with large governmental sponsored programs going into the UV and all the way up to the long wave infrared. Programs like VIRS and Landsat, they use this technology all the way up into the long wave. The drive for this is to make the systems have smaller form factor. They improve performance. They help bring overall costs down by not having to use different types of mounting and mechanical wheels and things like that. They also offer, in many cases, higher resolution and broader functionality, where you can kind of use a longer wavelength range. So there's two main types of multispectral array. There's one that we would refer to as a butcher block, where you coat an individual discrete filter really on any substrate material. You dice it up to the required size, and then you bond all those sticks together and then put on a dark mirror coating at the end. The other type is a monolithic array, where it's a single substrate. You go through a number of photolithography, coat, and then liftoff steps to get to the finished coatings that you want, and then you'll size it to the final size, and then put the mask on there. One of the drawbacks there is, with that single substrate material, you really don't have as broad a wavelength range that you can cover as with the assembled arrays. So with the assembled arrays, right now we've demonstrated up to 150 bands on one multispectral array. That includes many different types of substrates, from fused silica, zinc selenide, and even a lot of radiation hardened glass, all on the same multispectral array, which was put into typically on a window on a focal plane array. One added feature that the butcher block assembly allows is you can purposely make each individual band thicker to match the focal length that you're looking for. You can also bond multiple substrate materials together to help minimize the coating and take advantage of some color filter glass in there as well. So some of the capabilities that we currently have here is you can make filter segments to sticks as narrow as 20 microns. Typical bond lines are about 15 microns. The 15 microns, you can actually see the bond lines there. That 15 micron width we use is to provide OD5 band-to-band separation, which reduces channel crosstalk. We can certainly go down to what we call a vanishing bond line, where it's almost an immeasurable amount of opaque epoxy there. Edge chips for something like this, typically around 10 microns, but that's somewhat driven by the particular wavelength, the coating thickness, and the substrate materials you happen to be using. Again, typical coplanarity is about 10 microns on one side. You'll see on the next slide there are some options in the construction methods to actually make that even flatter and even in some cases have coplanarity on both sides. So there's a number of steps we do as well to control stray light, ghosting, and LAS. That starts right from the coating design, to the configuration of the layers, the material type, even the deposition process you use, all impact the type of stray light and ghosting you'll get. Same with the materials used. Both on the substrate side, not only the material used, but how it's prepared ahead of time, and then also the deposition process and the materials you use to build the actual coating. Assembly techniques also impact the stray light and ghosting, as well as the positioning and the type of dark mirror coating that's used. All of those combine to reduce stray light and ghosting. So as I mentioned, there's a number of different configurations. You can take that one stick assembly, cut it up like I was talking about before. You can also take it and bond it onto a window or a frame. Additionally, you can bond multiple substrates together as like a sandwich on that top. And then what you can do from there is you can polish both sides of that and then throw on an AR on either side. And now you have perfectly coplanar on both sides. And there's a number of other potentials here. These only show a few examples. And you can see down on the left side, most of what I've been talking about are that stick type configuration, but they can certainly can and are built in checkerboard configurations as well. So everybody's been mentioning yesterday about new space. I tend to refer to it as commercial space. The expansions and growth in this area have driven satellites smaller and smaller. Cost effectiveness now becomes a big part of the conversation. In the past, predominantly space was about science and exploration, and really the cost was somewhat secondary in that everybody just wanted what's the absolute best you can do. Now the conversation's more about, you know, how is it economically viable? How can you actually make money from this type of stuff? And even the government programs are looking to be more cost effective. Some multispectral arrays I see will be used 70-75% transmission in band, where, you know, in the past that was unheard of. Everybody wants 93, 95, 99, but now it's more the balance between the cost of what can be done and does it work for my application. Not so much it has to be the absolute best every time. So some of the things we've done here, because we have such a long history of involvement in this area, is we know, at least in the near IR and visible, what are the standard wavelengths that folks use for Earth imaging. So what we've done is we've selected a number of those wavelengths, and we actually kind of have those. I won't quite call them stock, but they're fully designed, they're fully qualified. You know, someone can call up, they don't have to spec a band. They can say, you know, we want band 5, we want band 7, and we now have that designed, and in many cases we have that on the shelf ready to be diced into whatever size somebody wants. The benefit of that is now you don't have to pay all the engineering for the different bands. You don't have to go through all the qualification. All of that stuff drives the cost lower and lower. Additionally, because it's already been qualified for those larger programs, you can kind of qual from similarity, which also saves more cost and time with these programs. So what's next? One of the things we've done recently is we're now building what we call a parallelogram array, where the sticks are diced at an angle to match the incident light coming in, which now further reduces the stray light and glinting on the edges. We're developing capabilities to build up to 350 bands on one particular butcher-block array. On the previous slide, I mentioned that we have standard near IR and vis bands. As more and more folks use bands in the UV all the way up through the long wave, those will now become more standardized, and we can come up with sort of a standard set for those as well. Now, another feature that's coming soon, large orders for a multispectral array in the past were 20 to maybe 50. I think the biggest we've ever had was like 100 of the same thing. Now we have requests for 1,000, 1,500, 2,000 of these things. As that number gets higher and higher, it's going to make sense to have automated assembly, automated inspection that will further reduce the costs and shrink some of that time, which is really key in the new space area. And lastly, we are certainly working on and have done some development on putting bands directly onto the detectors. There are some cases where that would be very beneficial in reducing further some of the size and weight capabilities, and then also assistive to reducing stray light and ghosting further. So with that, I'm going to thank everyone for your attention and open the floor for questions.